Hello, everyone. Welcome to another episode of True ML Talks. I am Nikunj, co-founder at TrueFoundry, and I'm super excited to welcome Jose Navarro, who is the lead platform ML platform engineer at Cookpad. Jose, it would be great if you can introduce yourself to the listeners here.
Hi everyone. Yeah, thank you very much for having me. I'm really looking forward for this conversation. So yes, as Nikun says, I'm the machine learning platform lead at Cookpad. I've been working at Cookpad for 4 years. For whoever doesn't know, Cookpad is the largest recipe service in the world. So it's a community where home cooking lovers come and upload their recipes, share their recipes, find other home cooking lovers, and yeah, we are making everyday cooking fun. So that's the main mission of the company. And yes, I work in the platform team, trying to help the machine learning engineers and all the ML practitioners to deliver ML systems quickly and reliably and valuable for our users.
Awesome, great. Thanks a lot for the intro, Jose. And by the way, I also love cooking, so I'm gonna try out a bunch of recipes in there. Yeah, it's gonna be fun.
Absolutely.
And to the audience, just a quick disclaimer: I'm not feeling very well today, so you might have a little bit of a thickness in my voice. All right. So Jose, to kick it off, you talked a little bit about Cookpad as well. Could you tell us a bit more about what does it mean to be an ML platform engineer at Cookpad? How is the overall team structure, with respect to the machine learning teams within Cookpad, and
Mm.
also what are the type of machine learning problems that you're trying to solve?
Yeah, that's a good question. To give a little bit of context to the audience, Cookpad is currently available in more than 80 countries and supports more than 30 languages, which is an important key challenge for delivering machine learning systems. I have been working at Cookpad for 4 years, and during those 4 years, the team structure has changed a lot. Because when I joined 4 years ago, what we had at Cookpad, it was a group of researchers focused mainly on greenfield research. So they were very good at researching with the data that we had available at Cookpad, and then publishing papers about new ways of understanding the recipe data, and a lot of interesting papers went out. But at some point, they were creating some interesting proof of concepts, and then the company wanted to help them delivering those proof of concepts into production. So at that time, the company hired me and another colleague who joined as a machine learning infrastructure team, trying to help them getting those models that were done in a Jupyter Hub, in an offline evaluation, and trying to deliver actual services that were able to support the type of scale that we have at Cookpad. Because one thing that I haven't mentioned is that we have more than 50 million monthly users. So it's quite an interesting scale that we have here at Cookpad, and also the challenge of multiple countries and multiple language also comes into play. So when we started in a team structure where we had the research team on one side and the infrastructure team on the other side, but that created quite a lot of interesting challenges as well, because the infrastructure team didn't really understand some of the challenges that the researchers were having to build those services quickly, and they didn't also have enough software engineering experience to for us to being able to deploy those services directly. So we had the usual common separation between devs and operations teams, where they basically were throwing over the fence systems that were basically they didn't scale, and they were not testable, reproducible, etc., etc. So we moved into a team formation where we formed a unique team. I created the machine learning team where we got together in the same team, same goals every day, talking to each other, collaborating in the same projects, and that helped us on both sides. Researchers became ML engineers after a few months, and the infrastructure team started building systems and tools and processes that were actually more um, a better fit basically for the machine learning engineers, to the point where we have quite a few successes with some machine learning projects at Cookpad, and we had some recommendation systems out there that they were quite heavily used and adding value to the business, and then the business saw machine learning as a potential new area now that was able to provide value to the business. And then we went through a transition where we split up the machine learning team because we had enough software engineering experience in the machine learning engineers that they were able to start collaborating in product teams end to end by themselves, because that's one of the key foundations that we said when we have this ML team is you build it, you own it. And then these machine learning engineers that were previously data scientists suddenly were able to understand the product and the user context and the problems that they wanted to solve, propose ML solutions, build it themselves, iterate over it quickly, and then create something that is actually deployable and productionize it, deploy it, and then maintain it and own it themselves and monitor it over time. So we have gone through a big journey with machine learning. So we are at that point at the moment where we only have machine learning engineers, and then we have a platform team that continue operating that platform and tools that helps them to create the machine learning systems as quick as possible and as reliable as possible. Sorry, that was a very long answer.
Oh, this is perfect. This actually sets things in context about how things have evolved over a period of time, and it's very very nice to hear that you all started from like a research engineering team, a research team basically, and like an infra team, and how the research team learned the skills of being an ML engineer, I guess, and they moved more and more towards learning software teams, and now you have reached a point where you have like almost like three different parts. Like you have ML team who are building out the models, then the platform team who is building out the tooling, and then the infra team that's managing the infrastructure overall. Is that right?
Um, well, the platform team operates the infrastructure as well, so we don't have
Oh, I see. Okay.
that was one of the goals when we thought about this team
Got it.
formation, but we failed to have that infrastructure base layer. So the machine learning platform team ended up operating the Kubernetes clusters and the AWS infrastructure that is all like the base layer, and the machine learning engineers are responsible for training the models, deploying the systems, operating them, maintaining them, agreeing on SLOs with product, and then making sure that they don't breach those SLOs. So like they build it, they own it. We just make sure that they don't have to care about what version of the Kubernetes cluster is or how do they deploy models into GPUs. They don't have to think about that because that's the responsibility of the platform team.
That's awesome. That's very good to know. And this you build it, you own it is a culture that we also used to follow at Facebook as well. So very strong advocate of this
Mm.
culture overall. One other thing is like how large is the machine learning team and the platform team overall roughly?
Not very, to be honest. So we have it's me and another colleague in the platform team,
Yeah.
and we have currently three machine learning engineers deployed into feature teams, but we are expanding or lowering the barrier of machine learning at Cookpad. So we're trying to get other software engineers that are somehow interested in machine learning to start being more involved as well. And we run a series of like seminars within the company to help with that. Um, But yes, so unfortunately, we had a bigger team, but unfortunately, at the beginning of the year, we, as many other tech companies, we went through some layoffs, and some people have
Yeah, yeah, yeah.
to they move on, and
Yeah, it's
but
the
yeah, it's
unfortunate reality of the tech world right now. Yeah.
yeah, absolutely.
Makes sense, yeah. And like you had mentioned one thing about like managing all the GPU infrastructure and all. Could you help us understand like what type of models are you building that requires the GPUs? Where are these like are these GPUs running on some cloud? Do you have like on-prem GPUs? Would love to understand what's
Mm.
happening with them. Yeah.
Maybe if you want, we can start with the an overview of the machine learning platform, and then I can answer more about details about the models and how we share GPUs on. We only operate in the cloud. We don't have on-prem, and we are in AWS. Apart from like a few resources in GCP for replication and stuff like that, but it's like 95% is AWS.
Right.
Let me show you. Let me show you quickly what the ML platform looks like in at Cookpad. What we
Absolutely.
build. So. All the user content and user actions that happened in the application, so all the new recipes or recipe additions, or when users dwell on a recipe, or they make a comment, or they make a bookmark, all those events are sent to Kafka, and we have all that data ingested through streaming services that process that data and enrich them, and calculates the features that we are interested in to train new models, or to run inference, and store them in the feature store from AWS Amazon SageMaker feature store. We also have Amazon Redshift as the data warehouse that we can also use to calculate some features in batches. But our main data flow is through streaming through Kafka. The main platform is based on is a microservice architecture on the top of Kubernetes that where we have some microservices that are able to take the requests from our users from iOS, Android, or global or web platforms, and then do the pre-process, and then send the request to our main inference layer, which is an open source tool that is called Nvidia called Nvidia Inference Server, and that's where we run our inference from. Then that's from the user's perspective, how they interact with ML. From the ML engineer's perspective, they have access to an experimentation platform that we build based on open source tools that they allow them to train models, to data exploration and some experiments with tools like Jupyter servers. We configure Jupyter servers in a way that they can request any type of compute resource that they require, including like big GPUs and stuff like that. We have Argo workflows so that they can run complex pipelines in DAX. We also provide Dask so that they can do distributed computing. And finally, we have MLflow, which is an experiments tracking and a model registry, and we use both sides of MLflow. So the usual flow of the models basically is an ML engineer starts working on a Jupyter Hub notebook to explore some data, train some models, and it tracks those experiments, and then they can collaborate with each other on the results of those experiments through MLflow, and then you can register a model in MLflow. Once the machine learning engineers register models in MLflow, we built some automation to be able to load those models that are registered in MLflow and then do some transformations and then load them directly in Nvidia Triton inference server. So an ML engineer is able to put a model in production just by training a model in the Jupyter Hub, collaborate with a colleague, making sure that the results are correct, and then registering the model in MLflow. And then our automation makes the rest and then moves that model from the model registry into Triton inference server, and then it's basically ready to start making some inference. So in terms of the type of models that require GPU, we have quite a few models for multi-language models, because as I said, one of the challenges is that we support more than 30 languages, and at the beginning we started developing each model per language, but at some point it became unmanageable. So we started looking into ways of doing representations of language with larger models through multilingual techniques. And those models are fairly big, mostly neural networks. One of the biggest models we have also is an image embedder. So a model that takes an image and then calculates some embedding features and store those features in the feature store, which is quite heavily computationally a bit heavy. So yeah, so those are the common use cases that we have. I mean, we basically, now that we are using Nvidia Triton inference server, we always default to deploying the models into GPU, because it's a technology that allows you to aggregate models into the same server. So yes, it lowers the decision. It makes the decision of deploying into GPU much easier, because deploying into GPU at the moment for us doesn't cost us any extra, because we're using the same GPU for multiple models.
Makes sense. This is very nice. Thanks a lot for helping with this and explaining the architecture. I think this is super nice. I have a few follow-up questions on the architecture. This gives a very good overview. So basically, when a machine learning engineer is experimenting, like they have access to a Jupyter Hub, which your team manages overall, and they can put different backends to the basically like different kernels on the Jupyter Hub, I assume, right? So and then they would run their experiments, produce the model, publish the model to MLflow, okay, and then the MLflow itself, then your team would take over from the MLflow model registry and take it through an automation pipeline. Is that right?
It's actually end-to-end automated. What we do is we have a list of backends that we support.
Yeah.
So we had a subset of backends that MLflow support and the ones that Triton inference server support, and then we say, okay, so which ones are the ones that in both systems are supported, and then we support in our automation, we support both of them. So there are a few, we have PyTorch, we have TensorFlow, we have ONNX, and a few others. So it's quite like everything. It's not all of them, but we tend to default to PyTorch or TensorFlow anyway, and ONNX for the for optimization neural networks as well.
Amazing. Wow, got it. So that's very helpful to know. And you also have the feature store here. So the question is, when the data scientist is running the experiments, are they usually pulling data from the feature store directly, or are they pulling data from some sort of a file storage system? Like, where are they pulling the data from, and how is the model overall capturing what type of features are getting used, so that in the online inference time you can actually invoke the same set of features?
Yeah, very good question. So in the experimentation phase, if they are training a model that uses features, if they're using features that are already in the feature store, then they have completely access to the feature store, and then they query the feature store in an offline, for example, if they trying to get a big batch of data, and then they get all the data, and then they reuse that those features. But if they are exploring new type of features, usually what they do is they have access to the data warehouse, and then they get the data that they need, and then they build the transformations that they want, and then they create new features, and then they train the model. And if the model is performing well and they're happy with it, then it's for them it's as simple as creating a new feature group in the feature store. We have a repository where we have like a schema where it's as easy as you add a new line, a new feature, and then you add this feature group is going to have this string, float 32, and blah, blah, blah. And then you add that schema. And then once that PR is merged, then we have automation that some AWS calls and then create that new feature group. And then the data that they used in the data warehouse is also flowing through Kafka. So the only thing that they need to do at that point is extending the streaming service that we have to consume the events that they require and do the same transformation, so that the features start flowing in a streaming mode into the feature store, and therefore they can use those features in online mode to do the inference for that model.
So basically, as I understand, like, this makes a ton of sense, by the way. So when they're trying to use a feature in the online inference time, they would extend the streaming service and, like, write whatever, like, small piece of code that consumes the Kafka events and produces the online features. Understood. Got it. And is there like a config that they have to maintain, or like somewhere it's maintained that what are the feature IDs that are getting used somewhere with each model?
When they register the model, they can add some information about the model and how it was built and the type of features that they use. And then the transformer gets access directly to the feature store. So these transformers can access to the feature store, and then they can have some configuration. If they do it through configuration, they can put the name of the features that they want, so that if they change the model or something, they can change it through configuration as well.
That makes a lot of sense. Two more questions on the architecture itself. So I think one of the things is you have also, like, talked about the reproducible training pipelines itself, right? That runs on top of Argo. So today, like, what's the workflow of, like, let's assume that a data scientist did some experiment that ran the model training itself, and they're like, okay, after they ran through a bunch of hyperparameter tuning, they're like, okay, this is the model that I think should just go through my retraining pipeline every day, right? How would they put that into, like, an actually running retraining pipeline on Argo? Basically, what's that workflow like?
We have focused a lot in the last couple of years in iterate quickly through new features, new ML features. So we haven't have yet that functionality that is mature enough in the app to say, okay, so let's have this retraining pipeline that replace or retrains the same model over and over every day or every week. What usually happens is that we have we still in iteration mode in a lot of the recommendation systems that we have. So we are it doesn't is quick enough before we even try a new model and we start A/B testing a new model and then we replace it. So we are still in an early stage with a lot of our systems in terms of ML. So we have the potential with Argo workflows to build reproducible pipelines,
right?
And but we still in early stage, and we don't have yet a reproducible pipeline, which is not ideal, to be honest.
No, it makes sense actually. Like, one of the things that I always like to call out to our users is that like, this is probably how you want to approach building out a machine learning system, that you lay out an architecture where these components are well thought of, that okay, like, when you need to, you can implement these systems, but you start much smaller. Like, you start with, like, simpler experimentations. you automate like one part of the pipeline that's more critical. So in your case, seems like inferencing was very critical, so you kind of automated that part. And later, like you have the component in place, and then you'll work on the retraining pipelines as well. This is actually pretty much like the most effective way of building a platform ground up. So like with a small team, the fact that you all are doing this in an organized manner is already amazing, and I think it's a great learning experience for everyone who's listening to the talk.
Absolutely, I agree 100%. And what happens usually if you go for the end-to-end system from the beginning is that you end up building things that you don't
Exactly.
need, or they don't exactly fit your problems, and you end up replacing things. Because right now I'm thinking that Argo workflows could be not the best way for us to build reproducible pipelines, because our machine learning engineers they know how Kubernetes manifest works, but Argo workflows are quite complex, and they get very complex very quickly. So I will try right now, if I tackle the reproducible pipelines challenge right now, I will try to use either Argo workflows with a Python wrapper on the top, or a different tool that is more Pythonic to build pipelines, because that will help the machine learning engineers to build those pipelines more effectively, and it fits better with our CI/CD as well.
Absolutely. Actually, you share a lot of sentiments that we hear in the MLOps community about the pipeline tools as well. So it makes a ton of sense.
Mm.
One last question on the architecture, Jose. By the way, this is super interesting. Like I'm loving this, like technical discussion around like how you have laid out the architecture and stuff. So
Wonderful.
you're using Triton inference server, right? Like Nvidia's Triton inference server. Tell us a little bit about this to our users. Like, what are the use? How did you decide to use Triton servers? How did What are the benefits? How are you able to effectively leverage this? Like people really want to learn about this usually.
Hmm. Triton Inference Service has helped us in three pillars. One is cost, because we very quickly realized that we wanted to run inference in GPUs, and running inference in GPUs on Kubernetes is a bit challenging at the moment. For whoever doesn't know, Kubernetes is very good if you want to deploy your services in CPU, because CPU resources are shareable in Kubernetes. You can request a portion of a machine, and then Kubernetes will give you that portion, and then it will share multiple pods into the same node. So you can start adding multiple apps in the same node, so you share the cost between different apps. With GPUs, is not the case right now in Kubernetes by default. You have to use other tools. It's a bit complex. I think there are some changes coming in 127 that will make things easier. But as for like last year, we wanted to deploy things into GPUs. And if you think about that, every app that you want to deploy, you have to request one full GPU. Is quite costly, especially in our case, because we have a lot of region-based models. Think about the recommendation systems in a region like in Spain. You have to build the model slightly different from what type of recommendations you're gonna do in Indonesia, because the features are slightly different. Like Spanish people, maybe they care more about one type of feature, so your models end up being slightly like region specific, or sometimes they are language specific. So for every app, if we want to deploy in our biggest markets, you end up with 6 or 7 models. So for every single ML feature, you need 6 or 7 GPUs. So that is the cost of that is massive. So when you, as a machine learning engineer or as a machine learning platform engineer, you are thinking about the benefits of the feature that you want to develop. You start thinking about the balance between the cost versus the business value that you're gonna get out. Like, how much value are we gonna add to our users versus the cost impact that is gonna have that feature in the business. And that's not nice. That's not a good situation to be. You just want to push things to add value and try to like not think about the cost, right? Which is the nice thing about Kubernetes with the CPU resources. So Triton Inference Server help on that side because Triton Inference Server is a platform where you can aggregate multiple models, and then Triton will register all those models in the same GPU and then share the GPUs between in the same node. So request comes in and they request different models, and then it's very clever about how and when to send the request to the right model, and saving those resources between the models. And then you have also interesting features to do batch requests or dynamic allocations to even, like, let's say that one of your models is more popular than the others, and then you can basically clone it and say, instead of one model of this, instead of one model, just deploy 3 models of this type, and then have more throughput on that model if your GPU utilization allows you that. So that's the cost. It's an important one. The performance is the straightforward one, right? Because if you don't have that, if you don't have to think about the cost of deploying models into GPUs, you by default you deploy models into GPUs, which is more performance. So your APIs, if your APIs are running inference live to end users, then you're gonna have much better performance and user experience. And the third benefit that we found, it was the user experience from the machine learning engineers, because before Triton Inference Server, we had a microservice type of pattern. We will wrap a model in a microservice and then have an inference server per model. So that means that for a new model, machine learning engineers will have to deploy a deployment, a service, a config map. They will have to build a few different Kubernetes manifests to be able to start running inference for that model. Whereas with Triton Inference Server, it's just a config map line that you can add just a new name of your model. And then because Triton is already configured with your model registry, in our case, it was S3, it will go and fetch that model and then load it. So those are the 3 main benefits that we find: cost, performance, and user experience from the machine learning engineers.
This is supremely helpful. I think this is one of the most comprehensive analysis of, like, why to use like an Nvidia Triton server. What are the advantages that you get that I've heard in a very long time. So thank you so much for sharing this. Um, One thing here, like, you talked about either using MLflow as a model registry, S3 as a model registry, right? So is it like, can you just directly pass in the model as is in that format in which you store in MLflow, and then, like, Triton will be able to spin it up as a service and scale up, or did you have to build a lot of pipelines around that, basically?
Yeah, so that was a nice addition that we had last year. From MLflow, when you register a model, the model gets pushed to an S3 bucket, and MLflow is opinionated about the folder structure, right? And depending on if it's a TensorFlow, it's pretty flat. If it's PyTorch, then it's slightly less flat. And then Triton, on the other hand, when you load a model, is expecting also a particular folder structure, where the files are, where the configuration files are. And MLflow and Triton have different ideas on how the models should be structured, right? So to be able to move a model that is in MLflow into Triton, you have to build a slightly, I don't think it's complex. It's just looking at the backend model that you want to support, and then compare the 2 folder structures, and then do some, like, files moving in with Python code. So it's not very complex. So we built that last year as a sidecar that we deploy next to the Triton inference server. So we deploy a small Python container that every minute is querying the API in MLflow, asking for what are the models that are registered, and then we make a call to the Triton API and ask what models are loaded, and then we reconciliate those. If we see that there is a model in MLflow, a new model that is being registered in MLflow that is missing in Triton, then we go to the S3 bucket, get the file, do some file movement to make sure that Triton is happy with the folder structure, and then we put them in the right folder in the volume of Triton inference server, and then we call the API to load the model. So that means that the model is suddenly loaded in Triton inference server, and you don't even have to restart the server. So you don't have to request a new GPU, wait for it to appear in your EKS Kubernetes cluster, and start up a new Triton inference server and then load all the models. You just basically call an API in Triton, hey, I've got new models, just load them, and then it loads it without
Wow.
having to restart it.
Thanks a lot for sharing this.
I'll
Uh,
make a note of that.
let's talk a little bit about the gorilla in the room, right? That is the new LLMs and the Gen AI. What's happening with all of that? So first of all, very curious to understand: are you all building some use cases on top of LLMs already?
We are exploring. We haven't built anything yet. We have gone through the whole security process to get permission from security to start using OpenAPI as a service, basically, because we want to make sure that we are compliant, and we have a few use cases in mind that we want to try. One of them is already on the way. We're trying to lower the barrier for users to create content in the platform, right? And writing a recipe takes some effort. Especially imagine that you are a busy dad, busy mom, and then you just cook some dinner for your kids, and then you feed them, and then you have taken all the pictures when you're cooking, but then you have to write the recipe after, write the steps, and that takes a little bit of effort. So we want to help on that, and we thought of different ways of helping with that, and we're gonna try to so using the voice recognition applications that are already on iOS and Android, get the transcriptions of a user, so a user can start talking to the phone while they're cooking. So I've got these ingredients. I'm gonna start frying the chicken or frying the onions or blah blah blah, and then you talk through it, and then using some LLMs as a service, send that transcription, and then ask them like, oh, could you format this text into a recipe following this schema, blah blah blah, and then we get those schema, and then um, move that data into the recipe form. So that hopefully lowers the effort to create recipes in the platform. But that's just one use case. We have like a lot of other type of use cases, like taking a picture on the fridge and then asking what can I cook, and then you recognize ingredients, and then we use our search system to propose recipes. We have ideas to build kitchen or recipes assistants, so that users can, if you are interested in a recipe but you don't have a particular ingredient, you can easily, using LLMs, ask them to replace an ingredient, or make this recipe so that I can cook it quicker, maybe, and then they suggest other tools. Or so we have a few different ideas, but nothing has materialized yet.
Amazing, awesome. Thanks for sharing these. And the first one actually seems super helpful. Instead of sitting down later, while you are cooking, talk through it. It's probably even more detailed. And I can imagine that an LLM can actually summarize it and organize it in a nice, neat format, structured data format. So
Yeah.
uh, that's very nice. Yeah. And one other thing that you touched on, like when you just started saying, is like you're going through some of the legal approvals to use the OpenAI APIs. Uh, some use cases that we talked about, right? Like where like recipes and structure stuff like that. I'm assuming this is a relatively more public data set. So did you also have to go through approvals for these, or like are these approvals like did you mean something else?
Um, Yes, I totally agree. So what we don't have sensitive data from users that we planning to send to LLMs. So what we will end up sending is like recipe titles, recipe steps, or things like that. But we have a security team, and they have a default process to for any third-party tool that you want to send data to. It doesn't mean that it has to be very sensitive. We have to follow that process and make sure that they are compliant with security and before we have the green flag to use it. Also, we operate in Europe, and Europe has a strict um,
GDPR
rules about how you use data, GDPR and stuff like that. And we have to make sure that we are compliant, and because we send in data, then my understanding is that it's not sensitive data, but then sometimes the boundaries between like it's slightly tricky, and yeah, you better be safe.
makes sense. Absolutely, you want to be like super safe with your users' data always. So it completely makes sense. Yeah. And like have you? I understand that it's not yet launched into production. Have you kind of like just tested the waters a bit, like tried out like how what kind of performance are you getting with these LLMs? Like let's say providing it some unstructured recipe and then asking it to organize into some structured recipes. Like is that something that the team has tried?
Yeah, we have a feature team working on it, and I still haven't seen it, so I can't talk a lot about it. But I mean, I haven't seen it in detail. I've seen a couple of examples, and then as expected, you get errors or transcriptions that haven't gone well. Then obviously the recipe probably is a bit confused, and then sends back some bad data. But in general, I think it's gonna help, and it's gonna speed up the process. So I think it will be interesting, but we will be user testing it very soon,
Makes sense.
with Cookpad users.
Awesome. Great. So this is very, very helpful. And like, from your perspective, like um, anything along the lines of like, that you do to keep yourself updated with what's happening in the LLM world, etc., that you want to share with the users?
I mean, in general, I attend to local meetups. I am the organizer of the MLOps community meetup in Bristol, and so I like to stay in touch with the community and talking to them and see how they uh solving problems in different ways. There is a community that I follow, which is part of the same MLOps community umbrella, that they started to talk more about LLMs as well. Um, yeah, that's mostly it, to be honest.
We love the MLOps community overall. And how is the overall like? Is Bristol like? Does Bristol has a very large community now in MLOps? I know that like each of the cities have like growing number of people, but very curious to hear about that.
We we have about 300 members now. So it's not as big as like New York,
Sure.
or cities like that. But I think for the size of the city, I think we rain constantly still. So yeah, and it's quite good. It's quite good. We always have a good turn up.
Makes sense. Absolutely. I think this is very, very nice. I think I want to ask you one last question, and which is around like you showed like a full-fledged MLOps architecture that you all are following, and like continuing to build on top of that, basically, right? So there's a lot of different components that you used from like your data processing, like initial experimentations, how you're using Dask, how you're using and then when you get to more production type of things, like you're using SageMaker and like Argo workflows, Nvidia Triton servers, etc. Right? So there's a lot of these components from experimentation to data processing to deployment, etc. You also have CI/CD and automation built in, right? From your perspective, what are some of the absolute must-have components that somebody who is building some sort of uh, real-time inference stack as well with MLOps should have in their component, like in their architecture, basically.
Hmm. Well, I think we touched before in terms of like tooling, and my idea always, I am not very tool orientated, so I don't think anybody should like recommend like the de facto MLOps stack. I think that should be a mistake, and I think my recommendation will depend a lot on the current maturity of the ML at that particular company. So when I joined, for example, we were very experimentation. So as you pointed out, we basically focus on delivering the models and the inference layer. Whereas if, for example, I talk to a company where they have a strong ML case and something that is already in production and is in the critical path, then reproducible pipelines will be quite key. Having make sure that and they have a feature store to make sure that they don't have features diverging from training to inference. Model observability will be an important piece to have as well, but it will depend a lot on the maturity of the ML,
Yes.
where they are at the moment, and do they have anything in production, or they don't have anything in production.
Yes. That makes a ton of sense. It's a very good way of looking at it. That like actually don't follow any must-haves in the MLOps stack. Let's go by your requirements and keep introducing tools as you need them in some way.
Exactly. I there is an analogy that I loved, which is that we as humans struggle a lot to solve problems by subtraction or simplification. We tend to solve problems by adding things on the top, and that sometimes is not the quickest path to solve your problem. Um, so, for example, I have a daughter, and I want to teach her how to ride a bike without the stabilizers, right? And when I was a kid, my dad taught me to ride a bike with the stabilizers. So I had a bike for a while with the stabilizers, right? And then I was riding that bike, and then when my dad took away the stabilizers, then I have to relearn the whole thing. Whereas my daughter have one of those like balance bikes, and then suddenly by replacing that stabilizers from the problem, you end up learning to ride the bike quicker. So sometimes by removing stuff or simplifying the problem, you get to the solution earlier. So not by saying like, oh, I need a feature store, so I need to spend 15 days researching what feature stores are out there and then doing proof of concept with all of them. Maybe what you need is to build a quick key value store with DynamoDB, and then get the project going as quick as possible and see if there is actually value in the feature that you're trying to build. Because if not, maybe you don't need a feature store right now. So why you gonna spend 3 months trying to integrate a feature store before even understanding if there is gonna add any value? So it depends. For us, that was the case. But maybe there is other company that has already a very strong ML case and feature out there that is in the critical path, and then you have to go straight away to like things like feature stores and reproducible pipelines and things like that. So it depends a lot on the case.
That makes a ton of sense. I think it's a very good framework of thinking, and you make such a good point about kind of learning and thinking through the subtractions and simplifying the overall like things that we're working on. So it's very very nice. Thank you so much, Jose, for for taking this time and explaining about how you have built out the ML platform, and what are the different use cases that you all are going after, and also some of the ways in which you generally like problem solving in life. So it's very, very nice. I really appreciate you joining us for the session.
Thank you very much for having me. It's been a pleasure.